All right, so chapter 28, problem 36. Loki, if you could please read for me.
In the circuit of figure BP, the switch S has been open for a long time. It is then suddenly closed. Determine the time constant before the switch is closed and after the switch is closed. Let the switch be closed at time equals 0. Determine the current in the switch as a function of time.
So, the switch is open for an infinite amount of time, right? Loki, what are we trying to find again? Help me. I'm just going to write it down.
Determine the time constant before the switch is closed.
Okay, hold up. So the time constant before the switch is closed. Okay.
And after.
Okay.
And then determine the current in the switch as a function of time. When the switch is closed at t equals 0.
Okay. After t equals 0, when the switch is closed. So let's just make sure we understand what's going on here. We have a switch. We have a capacitor. We have two resistors. This switch is open. So initially, what is going on here with this the switch is open?
Current is going through resistor 1 to capacitor and resistor 2.
True, and what's happening to the capacitor? We're charging the capacitor. So at time t equals infinity, with the switch open, we've gotten to the point where we have fully charged the capacitor. So right before we close the switch, what is the current in the circuit, Zach? No, it's actually not current max. So what is the current in the circuit, Jenkins?
0.
0, okay? Because we have charged the capacitor to its complete amount and we can't get any more charge to go across there. So before we close the switch at time t equals 0, there's actually 0 current going through the circuit. Then we flip the switch. What happens then? So,
I think the current will flow like backwards through the switch and at the junction of the current in both directions.
when we close the switch, we then start discharging this capacitor through this resistor. But what's the resistance class of the switch? 0 resistance. The switch isn't going to have any resistance. So this becomes discharging a resistor through this capacitor, and then we just have a normal circuit over here with a battery and a resistor, and we're trying to figure out the current through that particular wire. So let's now walk through the problem. We kind of have a basic understanding of what's going on. First off, the time constant before. The time constant of an RC circuit has dimensions, Miller, of? Seconds. What is the equation for the time constant of an RC circuit, Hillary? Time constant for an RC circuit. What's the equation, Emily? R times C. We know the capacitance. It's 10 microfarads. What is the resistance before we close the switch? Resistance before we close the switch. Jenkins.
150 kilo ohms.
Because
Because they're in series together.
we have two resistors in series. We have the 50 kilo ohm and the 100 kilo ohm in series. So 50 plus 100, or 150 kilo ohms. So we have 150 times 10 to the third multiplied by capacitance, which is 10 times 10 to the negative 6. Good luck. Time constant. I don't think it works out to be 0.015. 1.5. 1.5 dimensions. Seconds. In other words, when we have this circuit set up at the very beginning, it takes 1.5 seconds for what to happen? Silva.
63.28% of the
So it takes 1.5 seconds for the charge on the capacitor to get to 63.2% of its maximum charge. Good. The time constant after is also going to be equal to RC. But what is the resistance after we close the switch? Resistance after we close the switch, please. Garrett.
Not really sure.
Help him out. Who can tell me what the resistance is after we close the switch? Go ahead, Zach.
100 over 3.
Say again?
100 over 3.
It's not 100 over 3. Resistance after we close the switch for the RC circuit. Captain?
Is that 1 over 50 plus 1 over 100?
Just 0.
Nope.
Is that 100,000?
It is 100 kiloohms. Because after we close the switch, this becomes discharging this capacitor through this resistor. Because this, remember, has 0 resistance. So all the happy little anthropomorphic charges that are going this way, they're not going to go over here. They're going to go down here, every single one of them, right? Because there is 0 resistance here. So we're going to end up with current flowing this way. So the only resistor that these charges are going to go through is going to be the 100 kiloohm, or 100 times 10 to the third. Yes?
I don't know how much this matters, but why do they go that way?
Okay, here you go. You're the anthropomorphic charge. You ready?
Okay.
I am. I'll take the roll here. Okay. I'm going this way. I'm going this way. Right? I have my choice. I can go this way, where there's 0 resistance, or I can go that way, where there's any resistance. What do I choose? The path of least resistance. Okay? Because there's 0 resistance in that wire, I'm going to, every single charge is going to go down through the switch.
Every single one.
Every single one. Tim, what about the battery?
Does that affect?
Okay, so the battery is going to affect the number of charges coming through this wire. We'll get to that when we get to this part. Let me answer that when we get to this part right here. So
So like, I see where they pick the direction at the top junction, but then like, once they pass the switch,
yeah.
why-
Once they pass the switch, then it'll either go to the left or to the right. It doesn't really matter. So they actually do end up sharing charges, but it's the exact same number of charges that are going around this. If that makes sense. Because when they get down to here, they could go either way, because there is some resistance. I prefer to talk about it. Okay, so we have now times the capacitance, which is 10 times 10 to the negative 6, and unless I'm mistaken, I believe it's 1.0 seconds. Part A. Now, part B. No, part B. Part A had 2 parts.
Actually,
I'm sorry, the way I have it on the board. Leave me alone. Part B. What is the current? The current in the switch after we close the switch. Now, there are 2 different pieces of this. So the current through the switch is going to be equal to the current from the battery plus the current from the capacitor. Let's first figure out the current from the battery. How do we figure out the current delivered by this battery? Let. Okay, let me help you. Oh, hold up, let me help. No, no, it's not going to be. Let's do this one. Go ahead.
We got the voltage and another resistance.
Right. Therefore,
therefore, we really use that formula.
that one, yes, that one.
It's the voltage over resistance. I equals delta V over R.
How about we start with the equation so that we don't have to rearrange things. We know the electric potential difference equals the current times the resistance. Therefore, current equals the electric potential difference divided by the resistance. So the current delivered by the battery is going to be equal to the potential difference across the battery divided by the resistance. So the potential difference across the battery was 10 volts. Which resistance are we talking about here, Matt?
I don't know, is the resistance the 50 or whatever?
I don't know, is it? That's my question, that's what I'm asking.
I'd say so.
Okay. Because this resistor has no effect over what happens on this side, right? So we just have the 50 kilo ohms. So 50 times 10 to the third. So the current delivered by the battery is a constant current, and it has a value of
2 times 10
times 10 to the negative fourth, right? Okay. Or 200 milliamps, right? I'm sorry, microamps. 2.0, we'll do 2.0 milliamps. Okay. No, that's not right. 200 microamps, sorry. 200 microamps. Okay, so that is the current delivered by the battery. Now we need the current delivered by the capacitor. We have figured out the equation for this. We're not going to derive it now. We could if we wanted to, but we just derived it today. So somebody give me the equation for the current delivered by the capacitor. By somebody, I mean somebody in the room.
Negative current initial times e to the power of negative t over t.
The negative simply indicated the direction, and we know both of these are going to be in the same direction. We know the current is going to be going down. The current delivered by the battery and the current delivered by the capacitor are both going to be going down through the switch, so I'm not going to put the negative in there. We have R, we have C. That would be the time constant. We already know that's 1. We need the current initial. The current initial delivered by this capacitor.
Is it the same as the current delivered by the battery?
Is not the same as the current delivered by the battery.
Oh, well, the electric potential of the battery is the same as the electric potential of the
Notice, the electric potential of the battery is going to be same as the electric potential difference across the capacitor initially, right? Because initially, when we close this switch, there was 0 current flowing here, so both of these are going to have the exact same magnitude electric potential difference, which is 10 volts. Okay.
equals IR.
Okay, which is going to be equal to the current times the resistance. So this is the current initial multiplied by the resistance, which is going to be the 100 kilo ohm resistance. So the current initial equals the potential difference across the capacitor initial divided by the resistance of the 100 kilo ohm resistor, or what was it, 10? Yeah, 10 divided by 100 times 10 to the third, which I believe works out to be 100 times 10 to the negative 6th, or if I could do this again, 100 microamps, correct? So this ends up being equal to 100 times e to the negative t over, we figured out RC, it's 1, so I'll put negative t over 1, all of this in microamps. So when we add them together, we get 200 plus 100 e to the negative t, all of that in microamps. If you want sig figs, we'll do it this way. 0.200 plus 0.100 e to the negative t milliamps. Ha. So, graphing that. The current as a function of time is going to start, we'll do it in microamps. It starts out at 300. It ends at 200. It asymptotes at 200, and it's going to start here. where this part is the current delivered by the battery, and this part is the current delivered by the capacitor. Questions before we move on to numbers? Go ahead.
Are we allowed to just use the
This
or the,
right here.
Are we allowed to just memorize that and use it?
Here's what I will say to that question. No. However, you should have them memorized. How's that? Here's why. One, you're going to have to derive them, so it's good to have that, to know what you're deriving. Two, they come up often on the AP test where knowing the general shape and how they work is very helpful. For example, the free response question that I handed out today actually has the equation for current as a function of time. It gives you that and it asks you to find the charge as a function of time. And you should be able to look at that equation and figure out, for example, what the time constant is from the equation. So just as an example, you should know how the equations work so that you understand them. But yes, you have to be able to derive them as well.
So
And
that's-
no, you may not just pull it out. So if we were to have done this problem, the reason we did this piece, just pulled this out, is because we already derived this today. But if I were to assign this as a problem, for example, on a test, you would have had to have derived that. So,
So could you tell that the time constant's 1 because it's just like t over 1?
we already figured it out.
But like from the equation of the chart.
Oh, so if we were given this equation, we would know that the time constant was 1 because it was t over 9, correct?